So now the real calculus begins. This is one-sided limits. Limits are the foundation for all of calculus. So these are very, very important to our study of calculus and our understanding of how calculus was developed. So today we're going to talk about a specific type of limit, and that's the one-sided limit. So we're first going to learn the notation for one-sided limits, and then we're going to learn to evaluate one-sided limits graphically and numerically. We'll talk about what those words mean when we get there. But first, I actually want to give you a little idea about why limits are important. In the previous lesson, we talked about how to evaluate a function, find out what a function equals. Okay, well, I want you to look at the graph that I've drawn here. This is a function, or it would be a function. It fits all the rules. It would pass the vertical line test. But if you were asked to find the value of this function at -4, which would be right here where this vertical asymptote is, you would have to say it does not exist, because there's no function value here at -4. Well, if they asked you for the function value at -2, you would also have to say it doesn't exist. But this isn't a vertical asymptote, this is a jump. Well, what if they asked for the value of the function at 1, 2, 3? Well, you'd also have to say it doesn't exist because there's a hole there. And then if they asked for it at 5, you'd also have a problem. There's another vertical asymptote. So what I'm trying to point out here is that there are at least 4 places on this graph where the function simply does not exist. And if you were to simply evaluate it using an equation, all you would see for those 4 points is does not exist. But without a graph, that's not a very complete picture. This is a vertical asymptote, this is a jump, this is a hole, this is another vertical asymptote, but it's not the same as this one, because this one goes to positive infinity from one direction, negative from the other, while this goes positive from both sides. So if all you know is does not exist, again, you got to assume you're not looking at the picture. If all you're told is does not exist, you really don't know what's going on. Is it a vertical asymptote? Is it a jump? Is it a hole? Is it something else? Or what kind of vertical asymptote? Or what kind of jump? So that's where limits come in. So ultimately, limits' purpose is to describe a function's behavior, to describe what a function does. Now, limits don't care what a function is equal to, they only care what a function is approaching. So going back to our picture for a moment, it doesn't care that the function doesn't exist right here at x equals -4. What a limit will help you determine is that the function is approaching infinity from this side, and that the function is approaching -infinity from this side. The function doesn't actually reach infinity or equal anything at all at this point, but it tells you what it's doing as you approach it from one side or the other. Same idea here. It'll tell you you are approaching y value 1 right there, or right here we're approaching y value 2. We never actually reach it or touch it here, but that is what we're approaching, and that's what limits are designed to do. They don't tell you what's happening right at the point, they tell you what's happening around the point. So again, they describe a function's behavior, meaning just what a function does, and that limits don't care what a function is equal to, they only care about what the function is approaching. So we're going to talk today about one-sided limits specifically. And we're going to start by solving them numerically. That means using a chart or a table. We'll be using the calculator's table function to do this for us. So let's look at the notation. If you're not familiar with the word notation, it just means how we write things. You know that if there's an x with a 2 written really high above it, that just means x squared. That's the way we write things. So that's all notation means, how we write things. So first of all, this would be read, the limit as x approaches a from the right of f of x. The limit as x approaches a from the right of f of x. Or you can even say the limit of f of x as x approaches a from the right. Okay, and this would be the limit as x approaches a from the left for the function. So they're written like superscripts, so they're written the same place you would write a squared or a cubed, but it's a plus sign for from the right and a minus sign for from the left. So let's look at an example right here. The limit as x approaches 0 from the right of x squared plus 2. Now, listen carefully to the language there. It's from the right. So you have to think you're coming from over here on the right and then approaching what you want to find. Or if you're coming from the left, you're starting over here to the left of what you're going for, and then you're moving towards it. So from the right, from the left. So here we have x squared plus 2. So if you go to your table, excuse me, your y equals, you can plug in x squared plus 2. Now right now my table is set up so it just automatically gives me values. That's not what I want. I want to be able to put any value I want in there. So if you go to second, table setup, change the independent to ask and hit enter. Now when you go to your table, you can plug in whatever you want. So I'm trying to approach 0 from the right. So you got to think about a number line and think, what's to the right of 0? Well, 1's the first thing that might come to mind. But that's not real close to 0. Yeah, think about this number line right here. Here's 0 I'm pointing at. To the right of it would be 1. Now we want to get even closer. So maybe we'd say 0.5. And then maybe we'd say 0.1. And then 0.01. And then 0.001. And that should be far enough. So as you look, x is getting closer and closer to 0. 1, 1/2, 1/10, 1/100th, 1,000th. X is getting closer and closer to 0, while y values over here are getting closer and closer to 2. If you notice, if you highlight that 2, it's actually not exactly 2. The calculator is just rounding. It's 2.000001. So it's very close to 2. So this is telling us that the graph is getting closer and closer to 2 as x approaches 0 from the right. So our answer to our limit is going to simply be 2. Now let's do the same thing from the left-hand side. So we'll do the same function, but we'll approach it from the left. So same function in here, in y equals x squared plus 2. But now when we go to the table, we need to do things on the left-hand side. So I'm going to, instead of doing positive 1 and all that, I'll do negative 1, negative 1/2, negative 0.1, negative 0.01, negative 0.001. And again, we're approaching 2. As x gets closer and closer to 0 from the left-hand side, y is getting closer and closer to 2. Now this will happen often, but certainly not always, that it'll be the same from both sides. This is actually a really nice, clean function, x squared plus 2, nothing weird about it. So it's going to act really nice when it comes to limits. In fact, anywhere you picked on this graph, it was going to be the same from both sides. And going even farther, just think about what would happen if you plugged in 0. If you plug 0 in for x, 0 squared is 0, plus 2 is 2. So because this is a really nice, easy function, what the function equals and what the limit is are the same, but that won't always be the case. Okay, now let's look at another one. The limit as the absolute value of x minus 3 over x minus 3 as x approaches 3 from the right. So I will do the absolute value, go to math, number, absolute value, x minus 3 divided by parentheses x minus 3. Remember to put your denominator in parentheses. So first I want to approach 3 from the right hand side. So you see the graph over here. So you see something interesting is definitely going on right here at 3. So let's go to the table. Now 3 from the right hand side. So that would be like 4 and then 3.1, 3.01, 3.001, and I'll stop there because it's pretty clear that the limit is going to be 1. So I get a limit of positive 1 when I approach it from the right-hand side. Again, from the right, meaning I'm over here to the right. Here's x equals 3, but I start to the right of it and move towards it. Now from the left, I need to pick different values. Okay, to the left of 3 would be 2, 2.9, 2.99, 2.999, and so on. Very clearly you can tell the limit is negative 1. The closer x gets to 3, you can tell that y is just negative 1. So these two are different. And in fact, if you try to plug 3 in your function, you would get does not exist because the function can't have 0 in the denominator. So this is a case where what the function equals does not pertain to the limit. So the function doesn't exist there, but these limits do. The limit is 1 as you come at it from the right side and -1 from the left. So because they're different, that tells us we have a jump. I've got it pictured over here. We have a jump right there because the limits from each side are different. Okay, last example, let's look at this one right here. So we'll do the limit as x approaches 0 from the right of x over parentheses square root. Let's see, let me try that again. X divided by parentheses square root. There we go. X plus 1. And then you need to get out of the square root. Just hit right and then -1. The -1 is not in the square root. But then close the parentheses because we got to put parentheses around the entire denominator. So I am asked to approach it 0 from the right. So here I go. I approach 0 from the right. That'd be 1, 0.1, 0.01, 0.001. So you can tell that as x gets closer and closer to 0, y gets closer and closer to 2. So let's plug in 2. Okay, now this is asking us to use the same function. It's just using f of x to shorten it as we approach 0 from the left. So let's do -1, -0.1, -0.01, -0.001. So this, notice it's doing it from the different side, but it is approaching 2. It's approaching 2 from this direction as well. It's getting closer and closer to 2. So the limit on both sides is 2. But this is going to be a hole, and here's how I know how. If I try to plug 0 into this function, I'm going to get a 0 in the denominator. So the function does not exist at 0. But that's okay, I can still find the limit because the limit is 2. That tells us that what's happening is, if you look at the graph right here, as you get closer and closer to 0 on the x-axis, that is, you get closer and closer to 2 on the y-axis. But if you try to plug in 0, it's not there. Your calculator doesn't show holes, but there is one there. It doesn't exist at 0. But we know as you get really close to it, it's really getting close to 2. And that's what a limit really means.